Welcome to Monochemistry. Today we are going to look at an important concept called empirical formula. Now, I've got three little headings here for you, ionic, covalent, and uses. But before we do that, I'm just going to define what an empirical formula is. An empirical formula is a chemical formula that's written with the atoms and their simplest possible terms. Okay, so I'm going to go through some examples of that a little bit later on, but that's what it is. It's a chemical formula with atoms written in their simplest possible terms. Now, here's the cool thing about ionic substances. All ionic substances, every single one of them, are already empirical formulas. Sodium chloride, calcium carbonate, they are all already written in their lowest possible terms. Magnesium oxide. All of them. Every single one of them. Covalent substances, some are and some aren't. Okay, so for example, something like H2O, change my colors here, something like H2O, or something like CO2, those are already empirical formulas. Okay, so they're already written. They're chemical formulas that are already written in their lowest possible terms. But not all substances are that way, and I'll show you some examples here in a minute. Okay, the uses of empirical formulas. Well, empirical formulas are a huge part of a branch of chemistry called analytical chemistry. So let's say I'm a crime scene investigator and I go to a crime scene and I find a white powder at the scene of the crime. I take that white powder, and what I do with it, so I can determine what it is I put it into a machine called a mass spectrometer. Now that mass spectrometer will do a couple of things. It will determine the molar mass of that substance, and it will also give me the empirical formula of that substance. It will tell me how many, the lowest possible ratio of each atom in that substance. So it could be H2O, for instance. It could be CO2. It's probably not. It's a white powder. But that could be the ratio that it spits out at me. Now, once I have that and I have the molar mass of the substance, I can tell you exactly what it is. I can figure out exactly what the substance is. Okay, so it's a tool. The empirical formula is used in analytical chemistry to help determine the actual identity of a substance. Okay, so the lowest whole number ratio of atoms is what we're looking at here. Okay, so in this particular example, C6H14, the empirical formula for that, we'd have to look at the ratio. So right now, there's 6 to 14. Okay, so both of those numbers, I believe, can be divided by 2. And if I divide both of those by 2, I will get 3 and 7. That's the simplest whole number ratio of atoms in this case. So my empirical formula would be C3H7. Same thing for the next one. I have a 5 to 10, nice writing, Mr. Monahan, to 5 ratio. So therefore, I'm going to have, what can I divide that by? I can divide it by 5. So I'm going to have a 1 to 2 to 1 ratio. So it's going to be CH2O is my empirical formula. Okay, so that's how you do that. But now what we're going to look at is how to solve a problem using empirical formulas. Okay, so the question is, determine the empirical formula of a substance composed of 36.5% sodium, 38.1% oxygen, and 25.4% sulfur by mass. There are several steps to this. There's actually about 4 steps to this. The first step, when you get a question that's written this way, the first step is to go through and get the information that you have. Notice that it's giving me percentages. So that's how much sodium I have, that's how much oxygen I have, and that's how much sulfur I have. I'm just highlighting that. So the first step in this case is to do this. It's going to be to this is step 1, let 100% equal 100 grams. Okay? I need to figure out, I didn't tell you this yet, but I need to figure out how many moles of each of these things I have. And I can't do that with percentages. So mathematically speaking, the easiest way to go about getting a number of grams would be to let it equal 100% equal 100 grams. I could let 100% equal 10 grams. Wouldn't be as easy though. I could let 100% equal 50 grams. It doesn't matter. But this is easy. And that's why we do it. Because that way 1% equals 1 gram. So now that we've determined that 100% is going to equal 100 grams, we can simply take, and I've actually made a mistake here, we can simply take the percentages given in the question, which was 36.5 for sodium, 38.1 for oxygen, and 25.4 for sulfur, and we can assume that that's how many grams we have. Okay, so the percentage of each, since 100% equals 100 grams, is the same as the grams. Okay, now, as I said earlier, step 2 is going to be to calculate the number of moles of each of these things, and we're going to do that in a second. Okay, so step 2 is to calculate the number of moles. But before we do that, it's important to write out this part of the empirical formula. So remember, we're looking for the lowest whole number ratio. So what we're going to have is we're going to have Na with some number that we don't know, so it's going to be x. O with some number that we don't know, so it's going to be y. And S with some number that we don't know, that's going to be z. Okay, so our goal in this question is to find x, y, and z. And if I didn't say this already, you should copy that question down for your notes. And this is how you go about solving it. Make sure you go write the question, write step 1, step 2. Okay, so step 2 right now is going to be to solve for the moles. I'm not going to show how to do that because you guys already know how to do that. Okay, remember it's the mass that you see here, and you should use your conversion factor to solve. So on the next page, I'm going to show you what the mole numbers are. You should do the calculations by yourself, though. Okay, so we've calculated the moles. Make sure that for oxygen that you only used O, because this is a chemical formula. We don't know how many O's there are, so we have to assume that the molar mass of the oxygen is just 16, not 32. It's not O2, it's O. Okay, so if you didn't get the same number as me for oxygen, that would probably be Y. Okay, significant figures for this are 3. They're not as important in this question because what we're going to end up with is a whole number at the end, but I tend to stick to the rules, so there are 3 in the question, so I'm going to use 3 in here. Okay, all right, so that's step 2. Step 3 is to solve for x, y, and z. Oops. Solve for. Nice writing, Mr. Monahan. Okay, now how am I going to do that? I'm going to do that, okay? I'll show you an example. For x is going to be the number of moles I have for whatever is associated with x, in this case sodium, 1.59. And I'm going to divide that by the lowest number of moles from the ones that I calculated, which in this case is 0.794. Okay? And I get 2.0025188892. 2 is good enough. If it's 2.0, that's 2. We don't have to worry about significant figures now. Okay, so you're going to do the exact same thing. You're going to calculate y and z. You guys are going to do that. I'll show you what we get on the next screen. Y equals 3 and z equals 1. So that's step 3. Step 4 is to actually write the empirical formula. So you use the numbers that you calculated. So remember, we had NaX OYSZ. So I'm going to do that. I'm going to fill in, I'm going to substitute those numbers for what I had. So Na2O3S. But look at that. Does that look, and this is step 4, by the way, to actually write the chemical formula, the empirical formula down. Does that look like something we've seen before? What if I rearranged it? Could I get something that looked more like something we've seen before? That's what I want you to do. I want you to see if you can tell me what the name of this substance is. Because the way it's written doesn't quite look right. See if you can figure it out. What's the name of this substance? Now, a couple of quick things before I let you go. First of all, the numbers aren't always going to come out to be perfectly directly whole numbers. Sometimes you might get a 1.5 or a 2.6. So what will you do in those situations? We'll look at a couple examples in class where you have to manipulate those numbers a little bit. It's not hard, but it takes a little bit extra step. Okay, so there's 4 steps to this process. Step 1, let 100% equal 100 grams if you're given percentages. Sometimes you'll just be given grams, in which case you can skip that step. Step 2, find the moles. Step 3, solve for X, Y, Z. Hopefully you won't have too many more than that. It could just be 2, could be 3, could be 4, doesn't matter. Solve for those. And then step 4 is to actually write the empirical formula. And that, in a nutshell, is how empirical formulas work, what they're used for, and how to solve a problem. Bring your questions to class.